Thank you very much. Thank you very much for being here, and thank you to the organisers for putting together this wonderful workshop and bringing us all together. So what I'd like to talk about today is retrocausality, and more specifically, a strategy that has arisen in the Quantum Foundations community of using retrocausality as a way of restoring locality to quantum physics. So I should say at the outset that I am actually a proponent of retrocausal interpretations myself, but I think this particular motivation is not a good motivation. So in this talk, I'd like to explain to you why I think that is so, and also present what I consider to be a better motivation for retrocausal models. So I'll begin by explaining the details of this supposed retrocausal solution to the non-locality problem. I'll then discuss some reasons why one might be interested in local models in the first place, and I'll argue that the type of locality afforded to us by retrocausal approaches to quantum mechanics doesn't actually accrue many of the benefits one might hope to gain from a local model. I'll then switch gears a little and talk a bit about various ways in which we might fit retrocausality into a wider conceptual schema of the context of reality. And I'll argue there that really the only coherent way to do that is within a kind of all-at-once block universe picture. However, it seems to me that locality is more or less redundant within this kind of all-at-once picture, and therefore it doesn't really make sense to use retrocausality in this way to try and recover locality. Finally, I will discuss my proposed alternative route to retrocausality, which proceeds by accepting the existence of non-locality rather than trying to avoid it. So to begin with, the retrocausal solution is intended as a response to Bell's theorem, which, as you all know, says that quantum mechanics exhibits correlations in a Bell experiment, which can't be given a realistic intersubjective explanation in terms of a common cause in the past light cone of the measurements. So there must be some, if we want a realistic intersubjective account, there must be some mechanism other than a common cause going on here. So here's a very simple schematic diagram of the Bell experiment where the two particles are paired at A, they're then separated and measured at a space-like separation at points B and C, and then at point D, we bring the results back together and compare them. So basically, if we want to give a realistic intersubjective account here, we seem to have four main options. First off, we can postulate some kind of non-local, completely unmediated influence between B and C. We can postulate a mediated continuous influence between B and C that goes faster than light. We can postulate a mediated influence traveling along a continuous path that is partly retrocausal, so going either via A in the past or via D in the future. Or finally, we can deny one of the assumptions that goes into Bell's theorem, including possibly statistical independence. So the retrocausal influence, the retrocausal solution takes route 3. It says that if we give up on the assumption of no future input dependence or no retrocausality, we can get locality back by allowing our influences to travel via point B, D, or via point A. So there are a variety of ways in which one might do that. There are a variety of models, including the two-state vector interpretation, the transactional interpretation, Wharton's all-at-once models, and so on. But they all seem to have in common this idea that we can solve the Bell problem by using retrocausality to bring back locality. And I should note that some versions of superdeterminism, i.e. models which deny statistical independence, are actually also versions of the retrocausal solution, because the way in which they deny statistical independence is to allow some kinds of backwards influence from the measurement choices at B and C to the state preparation at A. So in that sense, denying the statistical independence can also be a version of the retrocausal solution. Now, it's important to note that the retrocausal solution doesn't give us back the full concept of locality or of local causality as that term was used by Bell and as it is used by some others. That's because local causality includes implicitly an assumption of no future input dependence. So Bell locality in its full form includes the assumption of no retrocausality. However, proponents of this solution will argue that the retrocausal approaches nonetheless allow us to recover a different notion of locality, which gives us many of the same advantages. So the notion that we do recover is known as continuous action. And we say that a model has continuous action if it utilizes space-time-based parameters associated with the intermediate regions between the preparations and the measurements. So all the correlations can be understood as being locally mediated, i.e. correlations can only be introduced or altered by intermediate space-time-based mediators which travel along continuous space-time paths between preparations and measurements. So the claim is that this idea continuous action is kind of what's really at the heart of locality. So as long as we can rescue that using retrocausality, we've done just as well as recovering locality or local causality in the normal sense. So I want to push back against that assumption, and I'm going to do that by enumerating various reasons that I can think of why one might want local theories in the first place. And so I don't claim that this list is exhaustive, of course, and if anyone wants to suggest any other reasons why one might want local theories, I'd love to hear those in the questions. So first off, one point that's often raised is we need local models in order to be consistent with relativity. So this idea is inspired by the fact that many extant non-local interpretations of quantum mechanics model non-locality in the form of an instantaneous wave function collapse or state update, which occurs everywhere at once. And the problem with that is, of course, that the state update or collapse must occur on some preferred reference frame, and that preferred reference frame will naturally look inconsistent with relativity. Now, these models don't necessarily lead to actual experimental contradictions with relativity because one can ensure that the preferred reference frame is not experimentally observable. But nonetheless, having this preferred reference frame in the model does look, at the very least, in tension with the underlying spirit of relativity and doesn't really seem like a very promising route to take towards unification. So they do seem like very good reasons to want to avoid postulating preferred reference frames. And moreover, it is true that these retrocausal models do succeed in avoiding preferred reference frames because these continuous paths carrying information through space-time are light-like and time-like paths. These are relativistically covariant objects, and thus we don't need to introduce a preferred reference frame to make sense of these models. However, if you stop to think about it, it's fairly clear that the mediation itself has nothing to do with the relativistic covariance. If we took one of those models, removed the continuous paths, and just allowed the events at the ends of the paths to depend directly on one another without any mediation, clearly that model would also be relativistically covariant. So adding in the continuous paths carrying information through space-time has nothing to do with the relativistic covariance here. That's simply achieved by avoiding having an instantaneous collapse everywhere, but there's no need to have mediation to avoid having that instantaneous collapse. So continuous action doesn't really seem to be doing very much for us in this sense. Relativity gives us no reason to prefer the continuous paths version of the theory over the direct dependence version of the theory. Another natural reason to want local models is simply the desire to make quantum mechanics look more compatible with our classical intuitions, because obviously we experience the world as being largely local. Maybe we feel more comfortable with local theories. But this, I think, is not a very good argument. We do certainly know by now that quantum mechanics must violate some of our classical intuitions, and there seems no obvious reason why locality should be completely inviolate, whereas, for example, apparently our intuitions about the direction of causality are allowed to be violated. So a better version of this argument starts from the observation that the macroscopic classical world, by and large, appears to be very local. So for instance, we can't send signals faster than light, we can't create instantaneous non-local influences, and all of these things are quite a striking fact about reality, which one might feel demands explanation. And moreover, one might well argue that the best way to explain these features is to say that the world really is local at a fundamental level. A slightly different version of this argument notes that the principle of locality has been very powerful in the formulation of quantum field theory. And although quantum field theoretic locality is not quite the same thing as Bell locality, nonetheless, one might think that perhaps the best way to explain the success of locality in QFT is to postulate that the world really is local at a fundamental level. So the problem with these arguments in the context of retrocausality is that this retrocausal mechanism has been proposed specifically as a way to allow us to create violations of locality, or at least apparent violations of locality in the classical world in the context of the Bell experiments. And thus, prima facie, there's no reason why these mechanisms couldn't be used to create much more widespread apparent non-locality. So, for example, if there were no restrictions on what retrocausal influences we could produce, then we could always produce the appearance of superluminal signaling by sending a signal forward into the future and then sending it back into the past to arrive at our desired endpoint. So that demonstrates that continuous action is not really what is doing the work in these models to explain the apparent locality of the macroscopic world, because that other model, which has much more widespread apparent non-locality, still obeys continuous action, since in that model, all the signals travel through continuous paths through the future and then back. So what's actually doing the work to explain the apparent locality in the macroscopic world in these models is simply the set of restrictions on the allowed backwards in time influences. Continuous action has nothing whatsoever to do with that. And therefore, a similar model where we remove the continuous paths, but keep the set of restrictions on backwards influences would offer just as good an explanation of the apparent locality of the macroscopic world and the success of the locality principle in QFT. So again, continuous action doesn't actually seem to be giving us anything very much of value here. Finally, one can imagine various arguments pertaining to ontology. So, for example, if one favors a particle-based ontology, it seems natural to want to keep continuous action in our theories, because kind of a defining feature of particles is that they're supposed to travel along continuous paths through space-time. So I don't think this is a very good argument either, because it doesn't really seem right that we should decide on our ontology in advance and then try to massage our theories to make them look compatible with our preferred ontology. Presumably what we should be doing is considering the totality of the evidence and selecting an ontology which is most compatible with all the evidence. And given the current state of quantum interpretations of quantum mechanics, I think it's certainly not the case that quantum mechanics very obviously indicates a particle-based ontology. So again, these ontological arguments on their own don't seem to give us much reason to choose models which obey continuous action. So I've argued that continuous action isn't really giving us anything particularly useful. I now want to switch gears a little and question the coherence of this whole strategy of using continuous action, of using retrocausality to recover continuous action. So to do that, I'm going to think a little bit about the ways in which retrocausality might fit into a wider conceptual schema of the content of reality, which is going to require making a couple of distinctions. So first off, I'm going to distinguish between what I'll refer to as a Humean approach to modality and a realist approach to modality. So the Humean approach says that modal notions like retrocausality and causality are only supervenient on the configuration of events in the actual world, which is to say things like causal influences and retrocausal influences are just descriptive. They don't really have power to bring things about. They just happen to feature in the most efficient description of what there is in reality. So if that's the kind of approach you take to modality, then you certainly can postulate theories which involve retrocausality, and you can make those theories have continuous action if you so wish. But there's really no good reason to do so, because in this kind of Humean picture, there are no gnomic powers, and so there's really no need for continuous action, because by ex hypothesized, these variables lying along continuous paths can't have any power to influence events along their paths. That is to say, in this kind of Humean picture, mediation and continuous paths can't be necessary to bring about the correlations, because nothing is necessary in a Humean picture. So going down the Humean route with these approaches to retrocausality looks like a very deflationary option, which significantly decreases the interest and import of the whole approach. And therefore, it seems to me, as far as I can tell, it doesn't seem like any of the proponents of these retrocausal solutions do intend to go down the Humean route. The alternative is some realist approach, which tells us that retrocausality is a feature of objective modal structure, and the objective modal structure is mind-independent and doesn't merely supervene on the configuration of actual events in the actual world. So within that side of things, I'm going to make a couple more distinctions. So I want to distinguish between two kind of notions of retrocausality that seem to be floating around in the literature. So first off, we have what I'll refer to as dynamical retrocausality, which is the idea that we have two separate, independent dynamical processes evolving in opposite directions. So that looks something like the two-state vector interpretation of quantum mechanics, where we have both a forwards evolving state and a backwards evolving state, and they're supposed to kind of meet in the middle and resolve some experimental outcomes there. The alternative is what I'll refer to as all-at-once retrocausality, where we have laws which apply all at once to the whole of the system or the history of interest. So the past affects the future, but also the future affects the past, and all this happens in a sort of all-at-once reciprocal manner. So we do have what one might refer to as retrocausality in the sense of influences from the future to the past, but there's no separating those influences out into distinct forwards and backwards directions of causation. So I should say at this point that I'm using the term retrocausality in a fairly general way here. So I don't actually want to insist that it's correct to use the term causal for these sorts of backwards influences. I think the question of the correct way to use the term causal in the presence of retrocausality is a very interesting one. But I don't have time to address it here. So in this talk, I will just go on using the term retrocausality to cover any sort of backwards influence from the future to the past, without necessarily meaning to presuppose that these influences really are causal. So I'm also going to distinguish here between two different notions of the way in which modal structure could play a role in shaping the content of the reality. So the first option is a dynamic production, which is a picture promoted by Maudlin, among others. It's a metaphysical picture where we think of the past as actively generating the future. So causal influences, in this sense, play an active role in producing one moment from the previous moment. This is most likely to be coupled with an A-theory approach to time, which regards the present moment as being kind of at the front of this process of generation as the universe grows. The alternative is what I'll refer to as block instantiation, where modal structure still does determine what happens in the course of history, but the selection of the course of history and its instantiation takes place eternally and timelessly in a kind of block universe setting. And so this is most likely coupled with a B-theory approach to time, where we're looking at this block universe picture and the present moment is not especially distinguished in any way. So first off, how would retrocausality fit in with a dynamic production picture? To start with, I think it seems fairly clear that we can't couple dynamic production with all-at-once retrocausality. And that's because dynamic production requires that the causal influences apply during the course of generation of the universe. So they have to apply while the universe is not yet fully generated. They have to work while things are not complete. But kind of by definition, all-at-once retrocausal influences involve laws which apply to the whole thing all at once. So we can't apply them during the course of generation. We have to apply them to the whole complete history or universe. So it looks like in the context of dynamic production, we're going to have to invoke dynamical retrocausality. But we still have problems with even dynamical retrocausality, because obviously, if we want to have both a genuine forward causation and genuine retrocausation, we're going to have to allow for some kind of dynamic production, both in the forwards direction and in the backwards direction. But the notion of production is an ordered one. It seems very natural to think that if one event produces another event, then the first event must exist before the second event in order to produce it. So in our universe, which has both forwards causation and backwards causation, it seems as though we're going to have the past existing before the future in order to produce it, but also the future existing before the past in order to produce it. So we end up with a kind of vicious circularity, and it's hard to see how the production process can ever get off the ground. One way to avoid that would be to invoke what I call mutable timeline retrocausality. So that terminology is taken from the philosophy of time travel. where we often distinguish between mutable timeline time travel, which is where time travelers can go back in time and can change the past and thereby change the present, as for example in Back to the Future, versus immutable timeline time travel, where time travelers can go back in time, but they can't change anything about the past because those actions have already been taken, as for example in Harry Potter and the Prisoner of Azkaban. So one can similarly imagine a notion of mutable timeline retrocausality, where we allow that retrocausal influences can actually reach back into the past and change things, and those changes get propagated into the future. And that would allow us to kind of make sense of dynamical retrocausality within a dynamic production picture, because we could imagine the universe being generated up to some time t, and at that time a retrocausal influence is generated, and that influence reaches back in time, changes some things, and those changes are propagated forwards, and then the universe can go on being generated from there. However, mutable timeline time travel is known to bring along with it a whole host of conceptual issues and paradoxes, and mutable timeline retrocausality inherits many of those problems. So for example, we have the famous grandfather paradox, where a time traveler goes back in time to kill his own grandfather to prevent his father's conception. And one can imagine a retrocausal version of that paradox, where I adjust some things in the present to create a retrocausal influence that will prevent my grandfather from being born, or whatever it is. So that's a clear danger of paradoxes as soon as we introduce mutable timeline retrocausality. Now, it actually turns out that, as Hugh Price has shown, the particular kind of retrocausality involved in quantum mechanics in these supposed retrocausal models is exactly the kind that would not be able to be used to create paradoxes like these. So we can cross the paradox problem off our list of issues, but we are then left with the issue of explaining how it is that these two apparently independent dynamical processes turn out to be exactly fine-tuned to each other in just the right way to prevent any paradoxes from coming about. The most natural way, it seems, to explain that feature is to postulate some kind of global consistency constraint. But global constraints are exactly the kind of thing that we don't have access to in a dynamic production picture, where these processes are meant to be happening separately and independently. Mutable timeline retrocausality also leads to a pretty strong form of skepticism about the past, because it's natural to assume that we ourselves witness events at the time when they are generated, which means we'll see the events happen before they have been adjusted by any retrocausal influences. But because the changes made by retrocausal influences must be propagated forwards in time, we will remember and have records of events as they are after being altered by retrocausal influences. So this approach implies that we have records and memories of a bunch of events that we never witnessed, that in a sense never actually happened, which leads to a whole host of difficulties around particularly things like scientific confirmation. And finally, there are also a whole series of well-rehearsed philosophical arguments against this idea of the universe being generated in some kind of quasi-temporal process, and those arguments will transfer in a straightforward way to arguments against this kind of dynamic production retrocausality picture. So all in all, it seems to me that this dynamic production picture coupled with retrocausality gets very messy and is extremely unattractive. And for that reason, as far as I can tell, it doesn't seem like most of the proponents of retrocausality, in fact, want to push dynamic production. And most of them seem to be more interested in a block universe, block instantiation picture. So how does retrocausality look in a block instantiation picture? Well, it's very straightforward to see how all-at-once retrocausality would work. We would simply have our all-at-once laws assigning probabilities to entire courses of history, then some particular history would be selected, and the block universe instantiating that history would just exist timelessly and eternally. But what about dynamical retrocausality? Now, it might seem tempting to say that we simply can't have dynamical retrocausality in a block instantiation picture. But that seems a little bit too quick, because many physicists today do believe in the block universe whilst also believing in the existence of dynamical causality in at least one direction of time. So there must be some way to reconcile those pictures. That's typically done by moving away from the notion of dynamical time evolution and towards some notion of dynamically possible histories, where our laws can kind of select the dynamically possible histories all at once externally in this timeless manner. So that works fine if we have only one direction of dynamics, but again, it gets very messy if we try to have two independent directions of dynamics. For a start, a history is not really an ordered notion. We can describe a history using forward dynamics, or we can describe the same history using backwards dynamics. There's nothing in the history itself to say which order is the correct one. And that means there's really no way to conceptually distinguish between dynamically possible forwards histories and dynamically possible backwards histories. But those are just two different sets of histories. So it's hard to really understand what it would even mean in this picture to postulate distinct forwards and backwards dynamics. Moreover, once we do that, we also have a pretty serious problem of figuring out how to reconcile these distinct and independent histories, because we have dynamically possible forwards histories and dynamically possible backwards histories, and then we somehow have to decide what actually happens, which unique history in fact gets selected. And it's hard to do that in a way that keeps the histories looking genuinely distinct and independent, because of course the forwards histories and the backwards histories must interact at each moment of time, and they become intertwined in such a way that regarding them as distinct dynamical processes looks very confusing. So this fact is sometimes obscured in presentations of retrocausal models of quantum mechanics, basically because these models often deal only with a single experiment. So in that case, we can easily imagine having forwards dynamics and a backwards dynamics which meet at exactly one point and determine exactly one experimental outcome. And that's all very clear-cut and easy to understand. But of course, in the real world, individual experiments must be embedded in some broader forwards and backwards dynamics. And whatever happens at that outcome in the middle of the experiment must have an influence both on the forwards evolving state and the backwards evolving state. And we have many such experiments all throughout time, all contributing both to the forwards evolving state and the backwards evolving state. And it becomes very difficult to figure out how to reconcile these separate dynamics. This problem is kind of pointed out by Maudlin in his objection to the transactional interpretation. He gives an example of an experiment in which the configuration of measurement devices at the end of the experiment is made to depend on some stuff that happens earlier in the experiment. And he shows that it's hard for the transactional interpretation to give a consistent account of this kind of experiment. Maudlin then goes on to say that he thinks this is a problem for all retrocausal approaches to quantum mechanics, basically because in order to make retrocausality work, you seem to need some kind of global coordination or global constraint to bring about consistency, and he thinks the retrocausal approach doesn't have the conceptual resources to do that. But in fact, taking a step back, it's clear that what Maudlin is really arguing against is a dynamical retrocausality, because of course, dynamical retrocausality doesn't have the kind of global coordination or global constraints which can be used to guarantee consistency. But all-at-once retrocausality certainly does. That's kind of the whole point of the all-at-once laws, that they apply to the whole thing at once and they ensure consistency between everything across time. So Maudlin's objection is really saying that we can't have dynamical retrocausality, and we do need all at once retrocausality in order to avoid inconsistencies. So in conclusion, it seems fairly clear to me that all at once retrocausality within a block instantiation picture is by far the most compelling and philosophically coherent way to implement retrocausality. And indeed, I think many proponents of the retrocausal model do agree with that. Wharton, for example, works in explicitly all-at-once context. Others often invoke the block universe. So this block universe all-at-once picture does seem to be reasonably well accepted. So the problem then is that in this kind of block universe all-at-once model, locality is redundant. The reason for that is that in an all-at-once model, probabilities are being assigned directly to the entire distribution of events across the whole of history, across all of the Humean mosaic. So there's really no need for information about one part of the mosaic to be carried to other parts by some physical variable propagating either forwards or backwards in time. That's because events at a point in physical reality in this picture don't actually depend on information that is present at that point. Rather, they depend on the all-at-once probabilities, which are assigned from the outside, so to speak, by by a process which can see everything at once and which therefore doesn't need propagation of information via continuous paths. So in this kind of all-at-once picture, you can technically add in continuous paths if you really want to, but they don't do anything. They're just descriptive fluff, which serves to make the model look more classical. So continuous action in the all-at-once picture, you can have it, but there's really no point, and there's really no interest to having continuous action in this kind of picture. Now, that said, I do think it's true that if you are dealing with an all-at-once model and you discover it's possible to create a local forwards time evolution decomposition of that model, that would be telling you something interesting about reality. So by local forwards time evolution decomposition, I mean, I suppose you try to decompose your model in such a way that the all-at-once probabilities can be built up from conditional probabilities at points, where the probability for events at a given space-time point is only allowed to be conditioned on events in the past light cone of that point. So if you can, in fact, build up the complete all-at-once probabilities entirely from these sorts of local conditional probabilities, that would be very non-trivial, and that would, I think, justify you in making some kind of interesting claim about locality. But what the Bell experiments are telling us essentially is that kind of local forwards time evolution decomposition is not possible in our world. So the retrocausal solution involves saying, well, instead of just having a local forwards time evolution decomposition, let's have a local forwards and backwards time evolution decomposition where we allow events to be conditioned on events both in their past light cone and in their future light cone. So the problem with that strategy is that the existence of that decomposition is completely trivial. That's because if we ourselves are going to observe any correlations, there must be at least one point in the intersection of the future light cones of the points between points at which the events involved in the correlation occur, because otherwise we wouldn't be able to compare the outcomes in order to calculate the correlations in the first place. And so for any correlations that we ourselves can actually observe, there must be a forwards and backwards local time evolution decomposition, because one can always achieve that by simply postulating a continuous path that goes forwards into that point in the future light cone and then back into the past. So demonstrating that you can find this local forwards and backwards time evolution decomposition tells you really nothing interesting at all, and certainly doesn't justify you in making any strong claims about locality in any sense. So this continuous action strategy is basically just constructing something which is entirely trivial and which tells us nothing very interesting about reality. So all in all, it seems to me more or less incoherent to try to use retrocausality of this all-at-once kind to try to recover some notion of locality. We just don't have locality if we have an all-at-once model. That's how these models work. So having said all that, I promised an alternative route to retrocausality. And given the discussion of the previous few slides, we're not going to try and rescue locality. Rather, we're going to do the opposite. We're going to accept that the EPR experiments involve genuine unmediated non-locality and see where that takes us. So in the EPR experiment, as shown here, we're going to take it for granted that there is some direct unmediated influence between the events, the measurements at B and C. We're also going to suppose, for the reasons discussed earlier in the talk, that there are no preferred reference frames in the universe, not at any level of reality. So even unobservable preferred reference frames are not allowed. So then note that there is no relativistically covariant way to decide whether the non-local influence in this Bell experiment goes from B to C or vice versa. Which entails that if we are not allowing preferred reference frames, the influence between B and C must be reciprocal. It must go both ways at once. B influences C, but C also influences B. We now invoke something known as the ontic equivalence principle. This is an idea that occurs in various places throughout quantum foundations, and it's simply the idea that when at all possible, if two processes produce the same operational statistics, we should assume those two processes can be attributed to the same kind of underlying mechanism. Now observe that in a Bell experiment, as on the previous slide, the operational statistics are the same whether B and C are at a space-like separation or whether C is put in the future light cone of B. So if invoking the ontic equivalence principle, we should suppose that the underlying process is the same in both cases. And given that we had a non-local reciprocal influence in the space-light case, we should also assume that there is a non-local reciprocal influence in the time-light case as well, which is to say, even when C is strictly in the causal future of B, C is still having an influence, a backwards influence on B. So we have genuine genuine time-like retrocausality there. So note that the retrocausality is not of the dynamical kind in this case, it's of the reciprocal all-at-once kind that we've been discussing over the previous slides, but it is a genuine backwards influence, so in that sense we do have a genuine retrocausality here. So to conclude, what does all of this mean for the retrocausal research program? For a start, I think the retrocausal research program will look much more compelling and philosophically coherent if they abandon all of these arguments based on restoring locality, because locality and retrocausality just can't be combined into a sensible conceptual model. Second, if we accept that retrocausality must be implemented via this kind of all-at-once holistic picture rather than via dynamical space-time processes, it follows that the retrocausal research program should be less focused on giving space-time descriptions of the retrocausal process. So many existing retrocausal models are quite focused on trying to give some description of the way in which retrocausality works in a detailed space-time way. So for example, in the transactional interpretation, there's a description of a process of echoes. In the all-at-once program, in Morton's all-at-once program, there's a description in terms of Lagrangians and pass-through space-time. In the two-state vector interpretation, there's a description in terms of two quantum states evolving through space-time. So the point I'm trying to make is that if we accept this all-at-once picture, all of these different models are really to be understood as different mathematical ways of describing the same direct dependence which occurs in an all-at-once way and not in a space-time dynamical way. So the retrocausal research program should perhaps pay less attention to creating detailed models of this process, which isn't really a process, and more to other problems like understanding the ontology of the models, and in particular explaining why it is that retrocausality is limited in the special fine-tuned ways we've discussed that prevent signaling and that ensure that the macroscopic world still looks largely local. And I personally think that would be a really interesting route for the retrocausal research program to pursue. So that's it from me. Do we have any questions?
Thank you very much, Emily, for this very nice talk about retrocausality. Yes, do we have any questions? I have one to start with, and we will see if there are follow-ups. So this, of course, is quite useful for accounting for locality or non-locality. Does the retrocausality explain also other features like contextuality, for instance? Is there sufficient?
Yes, a good question. So contextuality, I think, is best understood also as a fine-tuning problem. The question is not why do events sometimes depend on which preparation we used, but why is that dependence precisely covered up in such a way that it's not evident in the operational statistics. And that fine-tuning problem, I think, is very closely linked to the other fine-tuning problem I've discussed of why can we have non-locality but not signaling. And there are various different routes one might take to explain them. My preferred route is to think about this in terms of global constraints in this kind of all-at-once picture, and in particular to use global constraints which forbid closed causal loops. So that's a bit of a digression which would take some time to explain, but I do think these kinds of fine-tuned features of quantum mechanics really need to be explained by global constraints or by teleological reasoning. That's the only reasonable way to explain this kind of fine-tuning.
I see. Thanks a lot. Debashish?
So thanks for the nice talk. So I would like to ask that, so in a Bell experiment, we observed certain statistics according to the Bond rule. And does retrocausal model give some explanation on why we observe the probabilities according to the bond rule? Or
Yes,
yeah.
the retrocausal models predict the same probabilities as quantum mechanics, but they do that rather than having a kind of a collapse of the wave function as you might have in a standard quantum mechanical description. They instead have a message being sent via the future and back into the past, or alternatively back into the past and into the future. So the predictions are exactly the same, but the description of the underlying process is different.
Thank you very much. I think this is it. Thanks, Emily, again. We have to move on now.